In this problem, we're given that ABCD is a square with side length of 4. E is a moving point, and the square ECGF. Connect DF. H is a point on DF such that DH equals to FH. What is the minimum value of GH? So, first of all, to find the value of GH directly is going to be hard because we're given that we have two squares, ABCD and ECGF, and E is a moving point. If E is a moving point, well, that will mean that since ECGF is a square, DF is also a moving point. And since H is the midpoint of DF, that will mean that H is a moving point, which means that the line GF, the length of the line, is going to be uncertain. So we can't directly find it. Instead, we want to transform the line into something we can find. Since H is the midpoint of DF, well, this reminds us of a special property of triangles called the midsegment. The midsegment is the connection of the two midpoints of a triangle sides. And right now we're given one of the midpoints. So we should construct the other midpoint to see what we can do to find the length of GH. But before we do that, we are given that ABCD is a square. And then squares, they have a special property that their diagonals split the square into two isosceles right triangles. And then, after drawing the diagonal, we could then construct the midsegment. So, we just connect AC. So our first step was to connect AC. Then, we can't directly construct the midsegment. Instead, we can extend FG to intersect with AC. So we just extend FG. And we can call this point as I. And then, to complete the triangle, we just connect DI. And then we just need to prove that GH is a midsegment. So, first, extend FG to intersect with AC at I. Then connect DI. So after we connect DI, we'll know that our goal will be to prove that GH is the midsegment. And then to do this, first of all, assuming that we can prove that GH is the midsegment, what will we do? Well, DI is going to be a moving point on AC. And then when is I going to be on AC such that DI is minimized? That would be when DI is perpendicular to AC. Because if we have a point from a point to the line, the shortest distance is going to be the perpendicular line. So that will be how we could solve this problem. But first, we need to prove that HG is going to be the midsegment. And to do this, we have to use the properties of squares. First of all, since ECGF is a square, so angle IGC equals to angle FGC equals to 90 degrees. Since AC is the diagonal of square ABCD, so angle ACB equals to 45 degrees. This will mean that triangle IGC is isosceles right triangle. It will give us IG equals to CG equals to FG, because it's a square, ECGF. Then, since FG equals to IG, so GH is midsegment of triangle FID. Now we'll have GH equals to 1/2 DI. So we already know that DI is minimized when it's perpendicular to AC. So when angle AID is 90 degrees, then DI is minimized. And then we already know that by the property of diagonals, these are both 45 degrees. So we'll know that triangle ADI is an isosceles right triangle. And then the ratios will be 1 to 1 to square root 2. Since AD already equals to 4, so DI equals to 4 over square root 2. So the minimum value of DI equals to 4 divided by square root 2. And this equals to 2 square root 2. Which will give us the minimum value of GH equals to 1/2 2 square root 2, which is square root 2. And that is how you solve this problem.